Okay, good morning. Welcome back. Happy Monday. Today we're going to cover working with radicals. It's going to seem like this is a departure from our last two classes, which are about exponents, but very soon we will connect the radicals that we work with today with the exponents we've been working with the last few classes. Coming up in the not too distant future is our third quest. That's on November 1st. Questions on the calendar? Okay. So let's jump in here on page 126, and we'll start at the top. In this lesson, we simplify expressions that contain radicals. This lesson is a bit unusual in that we have two demos and two activities. So let's jump in with the first demo. So we know the square root of 49 is 7. And we know that that's 7 because 7 times 7 is 49, 2 copies of a 7. And that's why square root of 49 is 7. Similarly, what is the cube root of 64? It's 4, because 4 times 4 times 4, 3 copies of those equals 64. Okay, so some vocabulary illustrated in this expression right here, the nth root of x. That x right there is called the radicand. That's the thing that's inside the radical. That little n over there, that's called the index. It's telling us like how many copies of the number we're interested in, like a cube root of 64 said 3 copies of the right answer. And then the symbol itself is called the radical sign. Okay, let's take a look at this example here. Square root of 9 times 4, we're going to calculate that, and then we're going to compare that to the square root of 9 times the square root of 4. So for the first one, square root of 9 times 4 is definitely square root of 36, which is 6. Okay, that's the answer. There's no question about that. On the other hand, square root of 9 is 3, and then we're multiplying that by square root of 4, which is 2, and we get 6. And the answer turns out to be the same for both cases. And it is not a coincidence. Turns out this happens anytime we have multiplication with a radical. So the point here is that if you see a single radical with two things multiplied inside of it, you are welcome to split that up into 2 radicals and multiply them last. Over here, we did the multiplication first, right? 9 times 4, we did that first. Then we did the radical. Over here, we did the radicals first. Then we did the multiplication, and it turns out that you can do things in either order, and sometimes it's more advantageous to do one order over the other. So that's written out in this first part of the table. It's not just true for square roots, but for any root, any index. Multiplication works really nicely. Same thing is true for fractions, for division. Division inside of a radical, you could just as well, you could either divide first and then take the radical last, that's the left-hand side, or you could take 2 radicals first and then divide last. That's the right-hand side. And they're going to give you the same answer either way. Okay, let's take a look at number 5, which asks us to compare the square root of 9 plus 4 to the square root of 9 plus the square root of 4. This is the square root of what number? 13. Maybe somebody with a calculator can help us out here. 3 point something, I don't know, maybe 3.5-ish. How about the square root of 9 plus the square root of 4? That's really 3 plus 2, which is 5. Anybody have a more accurate answer? Okay, call it around 3.6. Did we get the same answer both times? No. What that means is that if you see the square root of something with addition inside of it, you cannot split that into 2 square roots. It's really tempting. Like, it looks like something reasonable to do, to just split that into 2 radicals. It worked for multiplication. It works for division. It does not work for addition. We just saw it. It does not work for subtraction. So if you see here in number 6, a radical of the form square root of x plus y or square root of x minus y, you can't do anything with it. You cannot simplify this thing right here. You cannot say square root of x plus the square root of y. You cannot say square root of x minus square root of y. Both of those are wrong. You cannot do anything like that. It's really common for students to think, oh, okay, square root of a squared plus b squared, that's just a plus b. But it isn't. You cannot split that up because it's addition inside of a radical. So not equal, wrong, wrong, wrong. Okay, we are going to simplify the fourth root of 48. So first of all, go ahead and grab the perfect powers table. It was that first sheet that we ripped off. Big old chart. It's got formulas on the back. I'm looking at the front right now. And looking for the fourth root of, for example, the fourth root of 81. Can we find the fourth root of 81 using our sheet? It's 3. Everybody see it? You look at the perfect fourth powers because I'm asking for the fourth root. And the fourth root of 81 is 3. How about the fourth root of 48? That's the question on the board. Is that in our chart? No. Fourth root of 48 is not a nice number. It's not a rational number. So we can't just write, equals 3 or equals 2 or anything like that. But we can simplify it. We're going to simplify it in a really particular way. And we're going to take advantage of the fact that we saw up above that multiplication inside of a radical is a good thing. So we're going to turn this 48 into a multiplication. What we're not going to do is this, fourth root of, give me a number smaller than 48 that's in that perfect fourth powers list. 16. Would you guys agree? Oops. 16 plus 32. Would you agree it's still 48? Yep. Can I split this thing up into two radicals? Fourth root of 16 plus the fourth root of 32? No. We saw we cannot split over addition. So even though the fourth root of 16 is nice, and even though this is a valid thing to do, we're stuck. We cannot split, and we cannot go any farther. But what we're going to do instead of breaking that 48 down with an addition, we're going to break it down with a multiplication. And there's a few different ways that you can factor the fourth root of 48. For example, would you agree that 48 is equal to 24 times 2? And then multiplication inside of a radical is really nice, and so we can split that up into two radicals, fourth root of 24 times the fourth root of 2. This is all valid. And then we look on our sheet and we say, is the fourth root of 24 anything we can find on our sheet? And the answer is no, 24 is not in that perfect fourth powers column. Looking for 24 in the perfect fourth powers column. And likewise, you're not going to find 2 in that column. So even though everything we've done is valid, we can't go any farther. So instead of factoring 48 willy-nilly, we're going to factor 48 with an eye towards those perfect fourth powers. So what you're looking for is a perfect fourth power, some number in that column that goes into 48. You see it? What number in that column goes evenly into 48? Perfect fourth powers column. We got 1, 16, 81, 256. One of those numbers goes in. 16 goes in. I said 1 goes in. Actually, 2 of them go in because 1 goes into everything, right? But factoring into 1 doesn't help at all. So we take 48, we rewrite it as 16 times 3. Yes, it's still 48. Then we use our nice property with multiplication and we say we are welcome to split this into two radicals. But then the fourth root of 16 is something really nice. Look at your chart if you don't know it. What is the fourth root of 16? It's 2. That's what the chart tells us. So the fourth root of 16 comes outside and becomes 2. It's not radical 2, it's just plain 2. And the fourth root of 3 we can't do anything with. So the fourth root of 48 is exactly the same as 2 times the fourth root of 3. And we say that the last expression here is simplified. So every radical that we see from this point forward, if it's got numbers in it, we are obligated to try to simplify it in this exact way. Look for the biggest perfect power that goes into it, and then pull that part outside of the radical. Okay, let's try the same game here on number 8. Square root of 12 minus 2 times the square root of 75. This one's written out right up above, but let's do the work right down here. So don't worry about the solution that's up there, but if you could copy here, square root of 12 minus, what was it? Minus 2 radical 75. I think we've got room right here at the bottom of this page to do it. Okay, so first step, is the square root of 12 a nice number? Is 12 a perfect square? No, we don't even need the chart to tell us that. So we do the next best thing. We factor 12 into the product of two numbers. And you could factor 12 in a couple of ways. You could do 6 times 2 or 3 times 4. Don't write this. It's still equal to 12. But is the square root of 6 anything nice? Is the square root of 2 anything nice? No. And so even though it's legit to factor 12 into 6 times 2, it's not helpful. But if you instead factor 12 into 4 times 3, is the square root of 4 anything nice? Yes, it is. And so that's why we factor it in that way. Subtract. Copy the 2. Copy the radical sign. Now, you might not know all that many factors of 75, but that's okay. This is not a question of, can you list all the factors of 75? This is, can you find a perfect square that's a factor of 75? So look in, don't say the answer out loud, even if you know it, but look in the perfect squares column right now on that sheet. And you are looking for a number that goes evenly into 75. Everybody see the list? 1, 4, 9, 16. We see it? Look through that list. What number do you see that goes evenly into 75? Jeremy? What goes into 75? 36 goes into 72. It's close. What goes into 75? Marianne? 25. 25 goes into 75. And so 25 is the factor that we're interested in. So we are going to rewrite 75 as 25 times something. How many times does 25 go in? 3 times. Okay? So it's not just factor the number willy-nilly, it's factor the number with an I on that list of perfect squares. Okay, let's keep going here. I'm going to use my nice square root property, which says square root of 4 times 3 is the same as square root of 4 times the square root of 3. And I'm going to do the same thing with the second radical, still copying the 2 that's sitting in the front. 2 square root of 25 times square root of 3. Okay, square root of 4 is 2. That is why we chose to factor 12 with a 4 in it. There's that moment right there. So we could pull that square root of 4 outside and make it plain 2. Not square root of 2, just plain 2. Minus. Okay, there was a 2 already in front. What is the square root of 25? That is 5. I'm going to put a 5 here without an operation at the moment, and I'm going to copy that square root of 3. And I've seen students do 2 different things with the 2 and the 5. I've seen students add them, and I've seen students multiply them. And only one of those things is correct. What's the implied symbol between the 2 and the square root of 75 originally? What operation is in there? That is a multiplication. Yes, it is not 2 plus. If we wanted to say 2 plus, you'd see a plus sign. But the fact you don't see anything means it's multiplication, right? Well, it's been multiplication the whole time. It's not 2 plus 5. It's 2 times 5. Okay, let's wrap this one up. 2 square root of 3 minus 10 square root of 3. And there is one last step. Because that square root of 3 is exactly the same in both, we can smush these 2 things together. It's like terms. Anybody have a guess? What do we think? That's the answer right there. Negative 8 square root of 3 is correct. I have also seen students try to do something funny with that square root of 3, like maybe add the 3's together and make a square root of 6, or subtract the 3's and get a 0, or multiply the 3's and get a 9. None of those is right. This problem right here is equivalent to 2x minus 10x, right? Square root of 3, same in both. X is the same in both. What is that equal to? That is negative 8x, right? You don't do anything with the x. The x is just like the thing you're counting. You have 2 of them, you subtract 10 of them, you have -8 of them. It's not x squared. X's don't cancel. We're just counting the x's. Okay, that's it. So yeah, so that's the simplified version. And if you were to type this thing carefully into your calculator and type this thing into your calculator, it would give you exactly the same messy decimal. And I would much rather deal with the second thing than the first thing, okay? That is how we simplify radicals. Any questions on that one? Okay, so let's skip this page right here and move on to the next page. So like I said, there's 2 different activities and 2 different demos. So let's see how far we can get on this page. The goal hopefully is to do all of them on this page before I call you back together to do the second demo. So let's continue on together, page 129. Here we go. So the second demo starts near the top. So we have seen earlier today that the cube root of 64 is plane 4. We're going to rewrite that in a different way. Would you guys agree that 64 is the same as 4 cubed? And so these 2 equations say exactly the same thing as each other. But in the second version of this equation, there's something some kind of cancellation that happens. I see a cube root, and then I see a perfect cube, right? I see a cube root and a cube. And in a very real sense, that cube cancels with that cube root, the entire radical, and I just get 4. You see it? The 4 is not the thing that's special. The thing that's special is that the cube root and the cube cancel each other. I could change the 4 to a 17, and the answer would be 17, right? It's not about the 4. It's about the cube root perfectly matching that power of 3. So for example, if you had the cube root of x cubed, and you cancel that cube root with that third power, what's left? X. X is the answer. Go ahead and fill that in. What is the 4th root of x to the 4th? It is x. So as long as the index, remember that's the little number in the front, matches perfectly with the power, then those 2 things cancel entirely, okay? All right, let's take a look at this next example here. Let's actually do this one out. So I'm gonna ignore the solution that's typed out there. So we got the 5th root of 32x to the 45th power. Let's see if we can't simplify this as far as possible. So would you guys agree? There's multiplication inside, and so I can take this and I can write it as 2 radicals multiplied together. Go ahead and copy that down. All right, is that okay? That's our multiplication property for radicals. Okay, the 5th root of 32 happens to be a nice number. If you don't know it, look on the chart. 5th root of 32, it is in the chart. Everybody look on the chart, find the 5th root of 32. It is 2. Everybody see it? Gotta know how to use a chart, because on the next quest, you will not have a calculator in your hands. You will have the chart. Okay, so we got the 2. I'll put a little dot for multiplication. Now we're going to clean up that 5th root of x to the 45th. So here's the tricky part. I'm going to copy the 5th root. I'm going to put some parentheses right here. And I'm going to ask, what power would I really like to see up here on the parentheses? I would really like to see a 5. I'm going to put a 5 right there. And if you don't understand why I'd like to see a 5, well, let me remind you, when we did the 4th root of x to the 4th, everything canceled except for the x, right? And the cube root of x to the 3rd, everything canceled except the x. So good things happen when the power matches perfectly with the index. The index is 5. It would be just so great if I could somehow make that power a 5. But the power wasn't a 5. What was the power? It's 45, right? It's not a 5th power. But it turns out we can still do something here. So go ahead and copy in here an x, and then give yourself a blank box. We're going to put a number in there in just a second. And this is the key. I would really like to put a number in here that gives me 45 x's, because that's how many x's I had before. we have a property for what to do with these two exponents, the box and the 5. What do we do with those when we smush them together? We multiply them, right? This is not the addition of exponents. This is the multiplication of exponents. So the goal is to put a number in the box so that when I multiply that number by the 5, I still get 45. It's the only thing I'm allowed to get. What is the magic number? It is 9. Put a 9 in the box. And even if you don't see exactly where the 9 came from, you have to agree this is equal to what it was before. Multiply the exponents, what do you get? 45. X to the 45th is exactly what we had before, so we have just rewritten in a much better way x to the 45th. And now, because we worked so hard to get that 5th root and that 5th power to be exactly the same number, they both magically disappear, and the only thing left is what comes out of this whole radical. Yeah, just x to the 9 is what comes out. That's it. 5th root, 5th power, cancel. All that's left is in black there, x to the 9th. And there was a 2 that was sitting in the front. Questions on that one? Okay, suppose that we just look at the starting power on the x, it is 45, and the ending power on the x, it is 9. What can I do with this 45 and 5th root to build the answer, which was 9? Can we just divide them? 45 divided by 5, that's basically how we got the 9. There is a shortcut there. We're going to talk about that shortcut officially next class, but for today, we are not using that shortcut. We are just building like we did with the parentheses in a blank box, okay? I also want to point out that it is sometimes tempting for students to think, okay, however I deal with the 32, I do the same thing with the 45. The 5th root of 32, that was easy. That's just a plain old number, it's just 2. The 5th root of 45 is not at all related to this question. I don't care about the 5th root of 45. What I cared about was building a 5th root and a 5th power, okay? So some folks are troubled by the fact that the 32 and the 45 get treated entirely differently. That's how it works. One of them is a plain number, the 32 sitting in the front. The other's a power. They are different. They're going to act differently. Okay, let's take a look at number 5. We're going to simplify the 4th root of x to the 20. Copy the 4th root. Give me some parentheses right there. What power would I really like to see on the parentheses? I'd really like it to be a 4. You just want it to match the index. Give yourself an X, give yourself a blank box. I won't say the answer out loud, but I want everybody to have a chance to fill in that blank box. There is one number that you can put in there so that you still have x to the 20. Go ahead and write that number in the blank box if you have it. And now say it out loud. What's the number? 5. 5 is the number. Because 5 times 4 is the 20. And then we've got all this cancellation. And what's our final answer? X to the 5th. No more radical. The 4th root and the 4th power all perfectly balanced. They cancel. And you just get x to the 5th. That's it. Okay, let's do one more together here. Cube root of 64x to the 27. Here, I'm going to split this into two radicals. Cube root 64 times the cube root x to the 27. Okay, cube root of 64 is nice. If you don't happen to know it off the top of your head, look in the chart. Cube root of 64 is 4. Okay, now I'm going to give you an opportunity to make a mistake. The cube root of 27 is also nice. If you don't know it, find it in the chart. What is the cube root of 27? It's 3. It is tempting, don't copy this, to say, oh, the cube root of 27 is just 3. And you put that there on the x and you call it done. That is not right. That's not right. The problem doesn't say find the cube root of 27. The problem says find the cube root of x to the 27. It's totally different. But I will give you the opportunity to goof up here because I'm a big meanie. Like, I didn't need to pick 27. I didn't have to pick a number that's a perfect cube, but you know I'm going to. But that isn't how it works. So let's do it the right way. Cube root, big parentheses. What power would you like to see on the parentheses? I'd like to put a 3 up there, so put a 3 up there. Give yourself X and a blank box. What goes in blank? 9. 9 is good because 9 times 3 is the same 27 that we had before. And now that we've got it in this great form, we're ready to write our final answer. Cube root, third power, all cancel. What's left? X to the 9. So 4x to the 9 is good. Questions on that? Okay, so the last problem in the demo is this one right here. We're going to simplify the cube root of 16x to the 4 times the cube root of 2x to the 19. It says here this will be tough. That is an understatement. I think that of all the procedures that we will do throughout the entire semester, this is one of the hardest ones right here. There's a lot of stuff going on in this one. It's all written out there, but I don't want us to just read. So can you join me on page 135? Go to page 135. And the reason I'm jumping to 135 is because it's got some space for us to do this problem out. So go ahead and copy. I've written it. I've taken a screenshot and put it up here. So this is the original problem. Cube root 16x to the 4 times 2x to the 9. 2x to the 19. Thank you. Okay, so we're going to work this one all the way out. And I realized actually the screenshot that I grabbed is not exactly the same as the original. Go back for just a second to the page we were on. What's the difference between the start and this one that I screenshotted? The other one, the starting problem, had 2 radicals. This is actually the first step. The one that I copied here is the first step. You had 2 radicals. You could simplify one radical, then simplify the other radical, then smush them together and make one radical, but you still have to simplify that third radical 3 different times. You'd have to simplify. Much better is to push them together right in the very beginning. You see 2 radicals multiplied, a good thing to try is to smush them together and make a single radical. So this is the first step already done for us. Okay, next up is we are going to combine the things that are like. So we'll do the 16 times the 2. That's 32. So we got cube root 32 x to the, what do you do with the powers? Add them. So x to the 23, yeah? 32x to the 23. We know we can multiply in any order, so we choose to smush together the things that are similar. Okay, let's go ahead and now split this back up into 2 new radicals. Cube root of 32 times the cube root of x to the 23. And it might seem like this is kind of heading us back the way we came because the problem started with 2 radicals, and the first thing I said was smush them together into a single radical. Well, each of the 2 radicals before had a number times x to a power. Well, this is better. These 2 radicals are better because one of the radicals is just a plain number. We'll handle that separate from the other radical, which is just a plain x to a power, okay? So we have done some stuff even though we're back to 2 radical land. Okay, let's deal with these guys separately. Cube root of 32. I could have given you this problem in the first activity today. Looking at your perfect powers sheet, is the cube root of 32 a nice number? No. So the next best thing we can do is look for a perfect cube that goes evenly into 32. There's not that many perfect cubes that we have to even try. 1, 8, 27, 64. Which one of those goes into 32? 8 goes into 32. So we are going to rewrite that one. Rewrite that one. Let's put it here as the cube root of 8 times something. What's the something to still have 32? 4. Okay. So right now I'm just playing with the cube root of 32. The x part, the x to the 23, that's going to be harder. We're going to do that after we finish dealing with this 32 here. So I'm going to keep going. There's blank space here because we've got to fill in what the x's are, but we'll do that last. We know that we can split this into cube root of 8 times cube root of 4. Yeah, that's our multiplication property. And then the cube root of 8 is nice. What is it? 2. So we got a 2, no more. It's not cube root of 2, it's just plain 2. And then the cube root of 4 is going to be in our final answer. We can't do anything with that one. So we've gone as far as we can with the cube root of 32. Now it's time to deal with that x to the 23. This is the hard part. Okay, let's go ahead and do this thing on the side here. Don't copy this just yet. But suppose that we played the same game we did right on the previous problems. And we said, hey, we're going to put some parentheses here. What power would I like to see? I'd like to see a 3 so that the cube root and the cube perfectly cancel, right? I'm going to give myself an x and a blank box. You don't need to copy any of this. The question is, can you put a number in there so that when I multiply by the 3, I get 23? Not an integer. I mean, you could put a fraction in there, you could put a decimal, but we are after integers. Really, really nice numbers. And we can't do it. The problem is 3 does not go evenly into 23, right? Like we didn't point this out before, but on all 3 of the examples we did before with x to a power, the power went, the index went evenly into the power. It doesn't in this case. Okay, so here's what we're going to do. We're going to think about taking that x to the 23. You don't need to write this part either. And we're going to peel one of the x's off. Would you agree it's still x to the 23? Right, still have 23 x's there. Now suppose that I forget about this x that I peeled off and I just look at the remaining 22. Could I put something in this purple box now to get a 22? The answer is no. 3 doesn't go into 22 either. So then we're going to try one more time. And we're going to peel another x off. So I've got x to the 21 times x squared. You agree it's still x to the 23? And now we look at the x to the 21. Can I build a 21 by putting a number in this box? Yes, I can. And this is the technique, is that you look at all the x's you have, in this case was 23 of them, and you ask yourself, can I put a number in the box so that I build 23 x's? And if the answer is no, you peel one of those x's off. We had 23, we peeled one off, we had 22. Then we started over. Can I build 22 with the number in the box? No, I can't. So I peel another x off, leaving 21 x's. And eventually, if you peel enough x's off, you're going to find something that works. And you want to grab the biggest thing that works. So let us do this in orange. So this didn't quite work. Okay, so this piece right here in orange is coming down here. We are going to rewrite that as the cube root of x to the 21 times x to the second. And there was a lot of behind the scenes calculations that went into figuring out why this was the right way to break up x to the 23. Okay, we're going to rewrite this as cube root of x to the 21 times the cube root of x squared. That's our favorite multiplication property from today. So we've got a blank there. The x to the 21 is the one that we have a little bit more work to do on, but the x squared is just copied straight down. There's nothing else we can do with that, and it will be in our final answer. we said we really wanted what power on this parentheses? We really want a 3. And so we put x in a blank box. And if I want 21 of them, what number goes in there? 7. Right? So all of the side calculations we did, they finally come to a head right here. Okay, equals. All right, x cubed, the cube root and the third power all cancel. So this whole radical expression becomes what? X to the 7. That's good right there. So I'll put that over here, x to the 7th. And we'll copy all of this stuff. We're finally ready to bring together the two different parts of our answer. And then the very last step of this problem is to bring to the front anything that's outside of a radical and push together into a single radical everything else. So here's our final answer. There's a 2. What else is outside a radical? X to the 7. And then instead of having 2 radicals, we know that when 2 radicals are multiplied, we can smush them together to a single radical. So what's inside of this single radical? 4x squared is good. So that's our simplified answer, 2x to the 7 times the third root of 4x squared. I promised you this was one of the hardest procedures of the semester. I was not lying. I think I need some Gatorade after that one. That was tough. I would ask if there are questions, but certainly there are, and the best way to answer those questions is for you to try stuff like this, but you will warm up slowly into problems like that. That's as hard as they come. So go back to page 130. Everybody back to page 130. And I'm actually going to make just a couple of changes to the problems here in the activity. Okay, so this first one right here, can you cross that one off and replace it with the 7th root of x to the 28th? And then after you do that one, you can actually skip B and C for now. I just want to make sure you really have time to do the harder ones, which are in this second table here. But instead of this square root of x to the 13, let's make it the 6th root of x to the 17th power. Try that. Okay. So what I want you to do is the first problem I just changed, and then I want you to jump down to the second problem I changed, and then continue in the second table. So only do that one in the first table.